The one time I actually got here early, and what time is it right now? It's like 7:20. Actually, I'm still earlier than usual. But anyways, guys, welcome to MCAT Physics. We're done with OChem. I kept my word where I said I was gonna finish in like literally 2 weeks. So here we are at Physics. And I'm surprised I'm even teaching physics, because physics, I'm sure like it's a consensus that it's everyone's least favorite subject, aside from cars, right? So, for the other 3 sections like Chem, Phys, Bio, and Psych, Soc, nobody likes physics. And I was the same. Like, I didn't like physics even when I was learning it in class. I don't remember anything from any of my classes, especially Physics 2. And so I was like, panicking when I had to do physics for the MCAT. But to be honest, it's really, really simple compared to your actual classes, right? Like, it's not that simple, but it's pretty easy to learn. Majority of the stuff, like 99%, just involves formulas and units, knowing when to use different formulas, knowing different unit conversions, all of those. And yes, there is some conceptual things, but some of the conceptual things can also be answered with formulas. But there's always gonna be something conceptual that like I personally will never know and you might never know. But for the most part, right, if you suck at physics, don't worry, just learn your formulas well and you'll be chilling. And I'm just gonna be going over like everything that I remember, including concepts, concepts, formulas, all of that. But I definitely recommend to like compile all your formulas in like a big sheet or several sheets, and then just practice writing them, because that will help you a lot. And for example, to elaborate on the units thing, maybe this is like a later chapter, but maybe you'll be getting a question and you have this passage, right? And they'll give you like 50 volts and like 10 centimeters. I don't even know like what the 50 volts is referring to, or 10 centimeters, but these are the only units I see. And then they're asking you like, what is the magnetic field of this and this? And they give you these answers, right? Like 10, 20, 30, 40, and then they'll give you this, newtons per coulomb, right? I know that newtons per coulomb is the same as volts per meter. So if I saw a question and I saw these were the units of the answer choices, and then in the passage I saw volts and like meters or centimeters, then I don't have to worry about no formulas or what the hell they're talking about. I just know I'm gonna divide this by the meter version of this and get my answer, all right? So that's what I mean by, you can take shortcuts for MCAT when it comes to physics. But yeah, let's elaborate on that. There's these things called SI units, right? SI units are just the standard units when you're dealing with formulas and stuff, right? So we all know that force equals mass times acceleration. But what is this mass? What is this acceleration? What if I'm given like 10 grams and like 50 centimeters per minute squared? This is a mass and this is an acceleration. But I can't just multiply these and get the force, right? Because there's specific units that we have to use, right? For mass, it's kilograms. For acceleration, it's meters per second squared. So let's like make sure we have the SI units down. It's pretty straightforward. There's not much to know. But for mass, it's going to be kilograms, right? Not grams. So kilograms. For time, it's seconds. For distance / length, it's meters. And then current is amps or amperes, however you say it. And then energy is joules. And then what else do we got? What is the SI unit for temperature? Yeah. It's Kelvin, not Celsius. And definitely not Fahrenheit. So for kilograms and grams and stuff, we'll talk about how to convert like from kilo to like giga or whatever. But really quick, for temperature, it's Kelvins. If you're given Celsius, all you have to do is add 273, right? So 273 plus your Celsius value gives you your Kelvin. So if your Celsius was like 29 degrees and you want to convert to Kelvin, just do 29 plus 273, which is 302 Kelvin. And then if you need to go backwards for some reason, 302 minus 273 gives you the Celsius. Thank you. So for units, prefixes and all that, right? I did this the very first class, right? It was Gen Chem chapter 1, but I'm gonna cover it over here as well. So base, when I write base, I'm referring to like like meters or grams or even amps. And then I'm gonna branch out to like kilo, centi, giga, all that stuff, and then the other way as well. So your base, I'll just put it as 10 to the 0, which is just 1, right? Let's go to the right, let's go bigger. We have, the first thing we have is kilo, which is just, hold on. Kilo, which is in K. And then next we have mega, which is capital M. And then giga. And then the last one is tera, capital T. So kilo is just 10 to the 3, mega is 10 to the 6, giga is 10 to the 9, and tera is 10 to the 12th. Now let's go this way. I'm gonna add some more other than like just 4. We have deci. Hold on. And then we have centi, milli, nano. Anybody remember the last one? What's after nano? It's very like uncommon, but just you know.
Is it pico?
Yeah, it's pico. All right, so can y'all see these? Am I writing big enough, by the way? These exponents. I made this mistake in Gen Chem chapter 1. I wrote super tiny. So for I'm gonna put this big line. All right, this is like your base. Once again, base means anything like grams, right? And I'm talking about like kilograms, megagrams, gigagrams, whatever, and then centigrams, milligrams, all that. For the right side, I think we all know what a kilo is, like it's 1,000. If you didn't know, just think about like, when you talk about I have like $1,000, you say I have like a K, right? I have like 2K or 3K dollars. That's like 1,000. For M, you know when rappers say I have 4 M's in my bank account, they're not talking about millions, they're talking about mega dollars. Mega is a million, right? 10 to the 6th. I'm just kidding though, obviously they're talking about million, but million and mega, they both start with an M and they refer to the same thing. So 10 to the 6th. And then after that, giga and tera. So, you know, the way I think about this stuff is, I mention this all the time, but what you can do is think about when you're buying a phone, right? What do they sell them in? 64 gigabytes, 128, 256, 512 gigabytes. And then the highest option, if available, is 1 or 2 terabytes, right? You're comparing like 100, 500 gigabytes to a single or just 2 terabytes. That tells you that terabytes is the largest one, then gigabytes come next, and then mega and kilo. You can also think of it like this. If you recorded a video on your phone and it took up 20 gigabytes, you're thinking like, why is it taking this much space? Like that's crazy, right? But if it takes up 20 megabytes, you're not really caring because 20 megabytes is nothing compared to 20 gigabytes. So you can also remember that order based off of that. And kilo, once again, 1,000. And it's pretty straightforward, right? You're just going in 3, so 3, 6, 9, and 12. Over here, deci and centi, or at least deci is not that common. I just included it because of this unit, decibels, but I don't think you'll ever deal with it. But deci is just 10 to the negative 1. Centi, we all should know, is 10 to the negative 2. Milli, also we should know. Now, micro, nano, and pico. Micro, it's just like, you know, if you take biochem or biology labs and stuff, you know, you'll be dealing with micro and milli values all the time. So I just make that association that micro is less. Nano starts with an N, so does 9, so nano and 9. And then pico, as I mentioned, like we barely ever see, so it must be crazy small if you're not using it that much, so pico is the lowest one. And you know, centi, or deci, centi, milli are like in order 1, 2, and 3. And then after that, it's the same thing as that side, right? We're going in 3, so 3, 6, 9, and 12. Now, if you're trying to convert from something to the other, like what I wrote here is a micro something is 10 to the negative 6th of the base, right? So let's say I'm trying to convert from here 10 to the 1 micrometers to meters, right? I want to go from this just to the base, the meters. What I'm going to do is put meters up here and micrometers over here. When I say that a micrometer is 10 to the negative 6th of a meter, I mean, that is the truth, but I'm not gonna put 10 to the negative 6 over here in 1, okay? I'm gonna put 1 up here, and basically I'm just trying to think like how many micrometers are in 1 meter. Since a micrometer is 10 to the negative 6, or we can say since it's 1 millionth of a meter, that means that I need 1 million micrometers to equal 1 meter. So this would be 10 to the 6, all right? And then you just, get the answer, which is 10 to the negative 5 meters. All right, does that make sense? So like, don't get this confused. This is just saying that this is 1,000th of a base or 1 millionth of a base. But when you're doing the actual calculations, you kind of have to flip it depending on how you're doing it. If you're doing it my way, then you have to flip it, right? You're saying there's 1 million micrometers in a meter. And then the other option would have been to do this. You have your 10 to the 1 micrometer, and then you keep 10 to negative 6 over here for meters, and then just put your micrometer here. Will lead to the same thing. One more thing I wanted to add was this one you should just know. A centimeter cubed, like 1 centimeter cubed equals 1 milliliter. But 1 meter cubed, anybody know what this equals for liters?
That was a kilogram.
What's up?
1,000 kilogram.
Just 1,000, I'm talking about liters.
Oh.
1,000 liters. I think you're talking about like water and stuff.
Yeah.
That's like density, which is different. But I don't know. Okay, let's just do something. I'm gonna show you how to convert from a cube to something else. Basically, like what you're gonna do here, I don't think it would show up, like it shouldn't, but just in case. Let's say I have 1 centimeter cubed here, and I wanna convert to, I don't know, meters cubed, right? So what I do here is 1 centimeter cubed, down here in the meter cube. Basically, how many centimeters are there in a meter? It's 10 squared, right? There's 100 of them. So I'm gonna put 10 squared. But since I'm dealing with cubed units, I'm gonna cube this, all right? So I'm gonna put 10 squared cubed, and then this will lead to like 10 to the 6 or like a million, right? So then you get like, or whatever, 1 over 10 to the 6. I'm too lazy, but you'll end up with 1,000 liters eventually. But that's just how you convert from like cubic things to the other stuff. Let's see. All right. Anybody seen Despicable Me? Have you? Nobody's seen it? Okay. I mean, if anybody has seen it, you already know what I'm about to talk about, which is vectors. All right. We have two things. We have vectors and scalars. The reason I brought up Despicable Me is because there's this guy named Vector, and he's always saying that vector is what does he say, bro? He says direction and magnitude. He says it in some funny way, but here's the thing, right? A vector involves magnitude and direction, whereas a scalar is just magnitude, no direction. So let me elaborate on what this means. Basically, we all know the terms velocity and speed, right? And you might have been told that velocity and speed are the same thing, they're interchangeable. They're really close, but they're not. Speed just means okay, I'm moving 5 miles per hour, right? So let me just write that out, 5 miles per hour. However, velocity includes a direction component. So I'm moving 5 miles per hour north, or 5 miles per hour southwest, or something like that. I'm gonna put north right here. But yeah, you'll see these a good amount. For vectors, another example would be displacement, whereas distance is a scalar. So I'll be coming back to this, but I just wanted to bring this idea up there of the difference between vectors and scalars. Once again, a vector is not just a value, it's also a direction, whereas a scalar is just a value, right? 5 miles per hour or 10 meters, all right? Next topic is gonna be, what's it called? Vectors, I guess. Yeah, vectors, but vector addition. Vectors are the very first thing that you ever talk about in a physics class. At least that's what I remember, right? I don't remember anything from physics. I just remember learning about vectors. That was the only part that I did good on my exam for that. It was just easy at the time. But basically, let's say I have a graph here. And I have vector going this way, and then a vector going here, this way. This is vector A, and this is vector B. If I want to add vector A and B, it's already in the correct orientation. Basically, this is called the tip to tail method. What you're gonna do here is line up A. So this is the tip, right? Like the part where the arrowhead is. And then tail means like the other side, right? So I have vector A here, and then vector B, I'm putting the tail right on the head. This is vector B. And then my sum will just be from this tip to this, or sorry, from this tail to this tip, so like over here. Right, it's like a hypotenuse type of thing. This is A plus B. You know, you'll get both the direction and also the value, so like, you know, whatever this equals. I didn't give any values. I'm not gonna spend too much time with vectors just because like vectors are not, I don't know bro, like, it's like the first thing you learn in physics, but I have never seen it anywhere other than like maybe one U-road question and like one third-party exam. But it's still good to know because it might help with other things. Now, when we're talking about just like a single vector, like let's just take this one right here. This vector, I'm gonna put like a 5, right? This is the value. This vector, it's going diagonal, and so it doesn't like, you know, this has two components. It has X and a Y component. So do these, right? Let's look at A, for example. This has an X and a Y component. The X component is this actual value, whereas the Y component is 0, because it's not going up at all. It's just flat, horizontal. For this right here, essentially, it's made up of, here, let me draw this plane. And then this, let's put 45 degrees for the angle. The X component will be right here. And the Y component will be here. All right? For this, what you're gonna do is, let's just say this value is like 5. Your X component is going to be 5 times cosine theta, and then Y is 5 sine theta. This is helpful when you're doing addition, so don't worry about solving this right now. I'll give you a question to solve. But since I brought the topic of cosine up, let me show y'all something. The trig method. I learned this on TikTok, and I even made a TikTok about it, and it's very, very helpful. Basically, you know, you're not gonna know like what is cosine of 60 or something off the top of your head, unless you're insane. So what you gotta do is you're gonna write, do you guys know the band, it's like the 1975? I used to listen to them, but 1975 is what you're gonna write up here, all right? 1, 9, 7, 5, and then just put a 0. This 1 means like the number 1, 9 means 0.9, and then 0.7, 0.5, and 0, all right? You're gonna start with the cosine up here, and you're just gonna go in order from 0, right? So 0, 30, 45, 60, and 90. This means that cosine of 30 is 0.9, cosine of 90 is 0, and whatever, right? Then under you can put sine, and it will just be backwards, so 90, 60, 45, 30, and 0. 0.7 is where they match up, but for everything else, or sorry, cosine and sine of 45 is where they match up, which would be 0.7. But yeah, sometimes they'll just straight up tell you like cosine of 60 is this, but other times they won't tell you, and you'll have to like know how to estimate. So they're not gonna give you some crazy shit like cosine of like 52 or something. If they do, you can still use this method and then just like kind of like round close to it. But usually they give you like easy numbers like 60, 30, 45, all of that. All right, now let me let's say I have a vector going like this and then a vector going like this. This is gonna be 10, and this value right here is 20. And then the angle with respect to the x-axis, I'm just gonna say it's 30, all right? So here's the thing. When you're trying to add something like this, like these two vectors, you have to add up all the x components and then add up all the y components, all right? So add all x's, add all y, and then you're gonna do square root of x squared plus y squared. So let's figure this out. I know this is really obnoxious, bro, like all this math. I don't even know why I'm talking about this, but it was in Kaplan, so let's just, in the odd scenario that you get something like this, it would be good to know. So for this one, your 10, this vector right here, its x component is 0, right? So let's put x equals 0, and then y, it's 10, y equals 10. Now for this one, the x component is going to be 20 cosine 30, and then the y component would be 20 sine 30. So based off of that, right, your x would be 20 times 0.9, which is like 18. And then this one, 20 sine 30 is 0.5, so like 10, all right? Then from here, I'm gonna add the x's. So total x, I'm gonna put xt equals 18. And then your y total would be 20. And then I'm not gonna solve this. I mean, yeah, I don't feel like it, but it's 18 squared plus 20 squared, whatever the square root of this is. That would be like your resulting vector. And you don't have to worry about doing the whole tip to tail method and all that. If you wanted to find the direction, you have to do some like inverse tangent stuff, but that's insane. So yeah, this is also probably insane too, but I just put it there just for fun. Yeah, now for vector subtraction, essentially, let's say I'm trying to subtract these, all right? I'm still doing the tip to tail method, but if I'm doing vector A minus vector B, I'm going to flip the one that I'm vectoring and then add it, all right? So if I'm doing A minus B, I'm gonna keep my A here, and then this B, I'm going to flip it. So instead of going up to the right, make it down to the left, right? So it would look like this right here, like that direction, and then you just bring it here, and then whatever this equals, it's just gonna be your A minus B value. So.
What is that piece that you went on the left, the 10 up and then 30 degree? So you said your y is 10 and your x is 0?
Yeah, because y is the up, like the horizontal vertical value,
right.
and then this is just up like that. It's not like curved at all. It's
right.
just straight up. So the x value is 0 for this vector.
Okay. 10. Then what about the 20?
The 20, this one is diagonal, so it has like an actual value for x and y. So you have to do for x, it's this value times cosine of the angle with respect to the x-axis, so 30 degrees. So I did this 20 cosine 30, and then the y is the same thing but sine. All right, now let's talk about vector multiplication. If you multiply this vector, let's say it's 5, if you multiply vector A by 3, you're just gonna get like a vector going this direction, but it's 15 instead of 5. And if you did like -3, it would be 15, but this would be flipped, right? So it would end up going this direction. Now there's dot and cross products, all right? So I'm gonna get rid of this. Cross products are the more like, I guess, useful one. But yeah, let's do, dot and cross products, all right? We have dot product, which looks like this, like a dot. And then this is going to produce a scalar. And the formula for this is, okay, so if I have, here, this is my A and this is my B. Let's put some values, hold on. Okay, if I was doing the dot product of this, A dot B, that would look like this right here. It would look like vector A dot vector B. It's just gonna be this, right? this is absolute value of A and absolute value of B times cosine of the degree that's, or the angle that's like between them. And this is gonna produce a scalar, so you're just gonna get a value but not a direction. Now, the other option is going to be called a cross product. So I'm gonna keep those same. Actually, no, I'm not gonna use those. I'll just, here, give me 1 second. Option 2 is cross product. Gives So let me give you an example. Don't worry, this will be fun after, let me put some things down. So I'm just gonna make it simple and put your 10 here and then just straight up. So the angle between them is 90, all right? And I'll call this A and this is B, all right? If I wanted the cross product, all I gotta do, what is sine of 90? It's just 1. And so I'm just multiplying. This is actually -10, by the way. But we're doing the absolute value, right? So -10, absolute value is 10. So 10 times 20 times 1 is 200, all right? This is my resulting vector. But I said vector. What direction is this vector going to go in when we're multiplying? This is where the right-hand rule comes in. All right. So what you're gonna do is you put your thumb in the direction of the first one, right? So here's the thing, right? I'm doing A, let's say I'm doing A cross B. A cross B is not the same thing as B cross A, all right? Keep this in mind. So we'll start with this one right here, A cross B. The first thing in this like equation is where my thumb is gonna go, all right? And then this one is where my index finger goes. So what I'm trying to say here is I'm gonna use my right hand and I'm going to match up with this. Can y'all see my hand? Okay. So and I also recommend y'all do this with me, but put your thumb facing the direction of A, so it's to the right or to the left. And then your B is going upward, so my index finger will go up like this. Are y'all following along? I don't even know if you can see this. Oh my God. What if I do it like this? Okay, whatever. So if you do this, look at where my palm is pointing. My palm is pointing into the page, right? So I have my A this way and B up here, and my palm is facing into the page. So my resultant vector will be into the page, all right? So it's gonna have a value or magnitude of 200, but it's going to be pointing into the page. Now look what happens if I'm doing B cross A. Now my thumb is pointing in the direction of the first one, which is B, which is up. And then my index finger is pointing to the left where A is, but look at this. My palm is pointing towards me or to y'all, right? So depending on which one you're crossing with which, your direction will change. And this right-hand rule, most of the time you use it for stuff with like electricity and stuff and magnets, but this will apply to that later, so it's good to know this for now. And once again, in the odd scenario that they give you a cross product with just regular vectors, it would be good to know it. Does anybody have any questions on that? Did that make sense? I don't even know if the video picked that up that well.
So do we always do A times B, or it just depends on the question?
You mean this?
Yes, like your thumb pointing towards A and then...
No, it depends. So basically, thumb is vector 1. So like this is vector 1, this is vector 1. Just depends on what's first.
Mm-hmm.
And then index is vector 2. Okay. And then basically, you know what you can do? Instead of palm, you can even
regardless of if it's A or B, whatever letter is first, that's what your thumb points to.
Yeah.
Okay. Interesting.
You guys get the same result when as what I did? Like, you guys got the out of the page and into the page, right? I'm gonna take that as a yes.
Sorry, quick question.
Yeah.
For the resulting vector thing, how would you say that, like, in words? Like, what would the answer look like?
So sometimes they'll just like, ask you the direction, and the options will be like to the left, to the right, into the page, out of the page, so you just choose the one that matches. I don't think you're gonna see this on the MCAT, but into the page they mark as X's, and then out of the page they mark as O's, but I've never seen this on the MCAT. Like basically into the page, like, you know, that way, and then this way is out of the page. But yeah, what I have seen is that the answer will straight up say out of the page or into the page. So displacement is a term we use, and it's generally delta x, and then distance is just x, all right? So displacement is a vector, right? And distance is just a scalar. So if I started over here, and let's say I went like you know, 100 miles, and I ended up in the exact same spot. Here, this is start, and this is end, right? The exact same spot. My total displacement, what is my total displacement? I started and ended in the same spot, but this entire path was like 100 miles. Let's just do meters to be SI units. My displacement would just be 0, because displacement is, it's kind of like, you guys remember path functions and state functions? It's kind of like that. But displacement is looking at change in direction. So it's a vector, right? So the direction you're going or the direction you're in actually makes a difference. But if I'm just talking about distance in general, and I started and ended in the same spot, but I went 100 meters, my distance actually has a value, right? So distance would be 100 meters, but my displacement would just be 0 meters or just 0. And then we were talking about velocity and speed, the same thing, but for like speed instead of position. So velocity is generally written as delta x over delta t, displacement over change in time, and then speed is just like distance over time. So velocity, once again, okay, for this right here, what would my velocity be? Technically 0 if I ended in the same spot, because my delta x would be 0. But for my speed, it just depends. Like if if it took me like 20 seconds to do this, right? 20 seconds to go 100 meters. Even if I started and ended in the same spot, I would have 100 over 20, which is 5 meters per second. Whereas over here, it would just be 0 meters per second. It's really odd, I know. Like you did all this motion, but then you ended up with the value of 0. But make sure you know that, all right? If you start and end in the same spot, your displacement overall will be 0. Because displacement, like think about it, displacement, like where is my change in placement? If I ended in the same spot that I started, I didn't really displace myself overall. Does that make sense? Here, I'll just bring it up now, I guess. We also have acceleration. I don't know what the scalar equivalent of acceleration is, but velocity, you can write it as like, delta v or just v. Acceleration is just change in velocity. Actually, this is just v. Acceleration is change in velocity over time, or change in time. So if I'm going like 100 miles per hour and then I'm ended up going 200 miles per hour and 300 miles per hour, I'm increasing my velocity, so that's called acceleration. If I'm consistently going like 50 miles per hour, my acceleration would be 0 because there's no change in velocity there. I'm just going the same speed in the same direction, all right? And make sure I didn't leave anything, because the next is what I'm pretty sure everyone is here for, which is like forces and all of that. Someone tell me, what is a force? Like, what does it mean? Basically, a force is something that changes the velocity of something else, right? So something that causes a change in velocity, all right? So think about, like, I don't know if y'all can see this table, but, or at least on Zoom, I don't know if y'all can see it, but like this table right here, right? If it was ice, like it's made of ice and I put a box on it and I pushed it, right? And there's no friction, no air resistance, nothing, all right? What's gonna happen? It's just gonna keep moving at the same speed. So maybe I pushed it to make it move 5 meters per second. It's just gonna keep moving at 5 meters per second. Until what? Until it either crashes into a wall or until someone touches it or somehow wind starts occurring. That stuff is going to change the speed, right? So it's going at 5 meters per second, but once I add something like another force, so it could be me like pushing it, that's going to change the velocity, all right? It might go now at like 2 meters per second, or it might go in 5 meters per second in the other direction, right? But that force caused a change in velocity overall. Remember, velocity is not just speed, it's also distance. What law did I just refer to, by the way? I hate these markers, man. All right. I just talked about Newton's, come on, someone fill in the blank. Which law? There's 3 laws. Newton's which law? First law. So Newton's first law is an object in motion stays in motion. Like you might have heard an object at rest stays at rest, but like the better way to explain it is object in motion stays in motion unless acted upon by external forces, all right? This is also like the law of inertia. Inertia is just something that keeps something moving. Anyways, right? By the way, I told y'all like a long time ago, for all of these laws, whether it be thermodynamic, Newton's laws, orbital stuff for chemistry, you should know what each of them refers to, all right? So that's Newton's first law. Next law will be the one where we get our force equation. So this is the one that relates force to mass and acceleration. You might have seen this, and you also might have seen this, F equals mg. A and g refer to acceleration. A is just acceleration as a whole, and g is gravitational acceleration. So you generally see it when you're dealing with weight. So like, for example, like if you look at me, right? I'll just make this up, like my mass is 18 kilograms and gravitational acceleration, it's 9.8, right? But for MCAT we round, so 10 meters per second squared, all right? So I am 18 kilograms, but the gravitational acceleration is 10 meters per second squared. So overall, 180, what's the units for force? This is like the most basic thing ever. Newtons, right? So let's just say me on Earth equals 18 kilograms times 10 meters per second squared. I would weigh 180 newtons. No matter where I go, I'm still going to be 18 kilograms, all right? Even if I go on Mars, Venus, wherever. But if I'm in a different place, let's just say me on the moon. I don't know what the G is over there, but 18 kilograms times, like, let's put 5 meters per second squared. On the moon, I would weigh 90 newtons, right? So you generally deal with like weights when you're talking about F equals mg, so stuff like this. And then this is just in general, like if I'm pushing something, depending on the mass and the acceleration, it could have different forces. If you think about a car, right? You have a car right here and someone is riding a just typical manual bicycle and they're going really fast. Is that really gonna cause much damage? Probably not. But what about a big semi-truck And it's not even going that fast. If you think of a big semi-truck and it just barely hits a car, it's gonna cause more damage. The reason is that semi-truck, has less acceleration, but the mass is so high that the force value is really high. Whereas a bicycle, I could be super, really accelerating, but the mass is not big enough, so the force wouldn't be high. You understand what I'm saying? This is Newton's second law. And then let's talk about Newton's third law. Get rid of this. All right, what is Newton's third law? Someone please tell me. Bro, this is like stuff you learn in elementary low-key. You might not know which one is which, but like you hear this stuff really, really early on. For every action, there is Bro, my little sister was telling me this the other day. What is it? Fill in the blank. For every action, there is. But y'all like killing me.
Equals opposite reaction.
Yes, the Zoom folks never let me down. So third law is for every action equals equal and opposite reaction. All right. So let me just draw a box. This box is me, and this is the ground. I'm not through the ground, I'm on the ground. All right. If I weigh 180 newtons. So I'm gonna put 180 newtons down on the ground. The ground is also pushing up with 180 newtons. All right, that's just like what it means. Weighing scales employ Newton's third law because the way I understand it is like when you stand on the thing, you're putting down like some weight, and then depending on it's gonna react with the same force, and then somehow it measures that stuff, and it gives you like your value. But just know that, right? It's a random thing, but Newton's third law is where weighing scales are, I guess that's what they're based off of. And the inertia one is Newton's first law. By the way, this 180 thing I wrote, this is called a normal force. It's just like, generally like normal force is the weight, but it's just that thing, right? Now, hold on. Not gonna make a difference. Are y'all good with this? I'm gonna erase this side. Okay. All right, now let's talk about friction. Friction is still related to forces. I'm just erasing for space. Friction is a force that opposes motion. So I'm gonna talk about inclined planes later on, but just as an example, if I have this inclined plane and I have a box right here, and I just let go of it, your box, because of gravity, is gonna be going this way. If this plane has friction, the frictional force would be acting on it in the opposite direction, right? The friction is going to prevent the box from moving or sliding down this way, okay? But friction is not always in this direction, right? The key thing here is that it opposes motion. I'm gonna draw the same thing. If I'm pushing this box, like I'm gonna draw like a person here, right? If a person is pushing this box this direction, right? This is the force that the person is pushing. Since friction opposes motion, frictional force will actually be going this way now, all right? It will be going down the plane. So don't just think like, okay, friction is opposing gravity. It's not opposing gravity unless gravity is the only force. But if there's actual motion, like me pushing this box up the slide, then the friction will just be in the opposite direction. There's two types of friction. We have static and kinetic. So static friction, the formula is going to be like very similar for them. But Static frictional force is just mu s times normal force, and then kinetic friction is mu k times normal force. This is it's called coefficient of friction. So coefficient of static friction or coefficient of kinetic friction, depending on which one it is. That's what this mu equals. Yeah, you know, you'll either be given a normal force or you have to figure it out, and they'll throw you the mu value, and then you use that to figure out some things. So when we talk about inclined planes, I'll like apply this. I mean, should I bring it up right now? Nah. Loki, I'll bring it up later. Yeah, but these are the values. What you should know, actually I'm gonna ask you, don't even relate it to physics. Is it harder to start a habit or is it harder to maintain a habit?
Start.
Yeah, that goes with it's like crazy how all the physics, but what the fuck physics relating to my real life. It's harder to start something than to continue it, right? Studying for the MCAT is probably really hard. Like, who wants to even dive into this monstrosity, right? But once you're in it, you're just you just have to deal with it. But it's really easy to maintain it, whereas it was probably harder to start it. Same thing, all right? Static friction means friction that's opposing motion at all, and kinetic is opposing the actual motion. So for example, that was horrible explanation. Static friction is the friction you have to overcome to actually cause motion. So right now, let's say this box, it's not moving, all right? I know it's on an inclined plane and gravity's pointing down, but let's just say it's not moving. Why is that? Because there's static friction, all right? Once I move the box enough and I overcome that static friction, I'm still dealing with friction on this plane, but it's a different type of friction. It's kinetic friction. And those frictions are not the same. Static friction, it required more force to overcome it, whereas kinetic friction, it requires less force to overcome. For the same reason, right? It's just harder to start something than to maintain. So the most you have to really know is that static friction would just be higher than kinetic friction, or in other words, mu sub s would be greater than mu sub k, because Fn is gonna be the same thing. But usually, when you're dealing with inclined planes, we talk about kinetic. So yeah, that's all I'd say to know between static and kinetic. All right, you know what? I'll just bring it up now. Inclined planes. Let's do a flat plane real quick. So this plane, once again, the weight of the box is here, and Newton's third law tells us that it's pointing up as well. So this is Fn, which is just mass times gravitational acceleration. This is also the same thing. They equal out. If this didn't equal out, then this thing would be floating, right? Or going through the ground, so they're equaling out. Now I have a person pushing here. So I'm pushing this way. This is gonna be, I'm gonna put motion force. This F, right? F equals ma. And then if there was friction, friction is going this way. So what is friction? Let's say, okay, I'll give you some values, all right? Mu sub k equals 10, I don't know what the units are, I don't think there's a unit. Mass, 10 grams, and then, yeah, that's it. All right, what is the frictional force? This red one, what is the frictional force based off of what I gave you? I use the number 10 and 5 so much. Anybody get anything? Let's figure this out. Basically, let's figure out what the normal force is first, right? Mass times gravitational acceleration. This is 10 grams, so 10 grams. Damn, bro. I'm not gonna throw that one this time. All right, 10 grams. If you're trying to convert it to kilograms, right? There's 10 to the 3, so it's just, dividing. So 10 to the negative 2 kilograms. We have 10 to the negative 2 kilograms times the gravitational acceleration. I didn't give it because you should know it. 10 meters per second squared. This will give you 10 to the negative 1, or we can just write 0.1 newtons, all right? That's our normal force. Now I said this is our static friction, or whatever, kinetic friction coefficient. Just use this formula. You have your normal force, you just multiply that, right? So if you multiply this, you're gonna get 1, so 10 times 0.1 gives you 1. And I'll put force K, all right? This is kinetic friction force. So this is the force going in this direction, all right? So the reason I bring this up is just to show you how you solve it, right? Because when I include inclined planes, it's gonna be the same thing, but with like cosine and sine. So just like, I guess, prepping you.
So 0.1 newtons would be like the force that's like opposing the movement, right?
No, what is 0.1?
Your frictional thing, right?
No. So this is going to be your normal force. So because I converted.
Oh, right,
yeah.
right. And then you do 0.1 times 10.
Yeah.
To get your force that's opposing the movement, right?
Also, before anyone calls me out for making this unrealistic, look, yeah, I'm pretty sure your coefficient's usually a decimal because this is kind of a high value, but I'm just doing this for practice. Don't worry about like realistic stuff or not. All right, ready for inclined planes? So I have this right here. I'm gonna draw a box. Try to draw this big. So this mg stuff, it's assuming like there's no, cosine, sine to deal with, it's just one. But when you have an incline like this, you have to include, remember the whole x and y component of a vector we were talking about? It's kind of like that. So for your normal force, instead of just m times g, you have to do m times g. So I'll put mg cosine theta. Theta just is this right here, whatever this angle is. All right. So that's gonna be your normal force on the box in that direction. All right. And then same here, same thing, Fn. Now you're also, you have gravity pushing you down, right? Don't worry about friction and all that. If you leave a box on a frictionless inclined plane, it's gonna slide down. Why? Because of gravity. So there is a gravity component there. This is going to be, if it's not mg cosine theta, it's going to be mg sine theta, all right? Now, how do you remember this? Okay, don't even ask me where did we get sine from and cosine from. I'm good at math, but like my brain just stops working when it comes to this. Just know sine is the one that's sliding down, right? Sine is the one that's causing me to slide. Sine and slide, they both start with S and they have the I. So sine slide. Cosine is just the other one, all right? I always like mess this up, got confused. Just that's all you gotta know. Don't know why this is sine, why this is cosine. Just know sine is this one, right? The one that's parallel, and cosine is perpendicular. So what would be the equation for the kinetic friction force based off of this inclined plane, or just inclined planes in general? What would be the equation for that? Very simple, guys. All you gotta do, right? This is our normal force, and I said normal force times mu sub k gives you kinetic friction. So instead of, like if you want to write the entire thing, you would have mu sub k times mg cosine theta. Does this make sense? These are the different forces. And once again, I put this force facing that direction if I'm assuming that gravity is pulling down this way. But don't forget, like if I have a person pushing this way, like up to the left, then my frictional force would be down to the right. I'll give an example with that in a little bit. All right, it's time for a question.
Wait, so does that mean that your normal force would basically just be equal to your mg cosine theta?
Yeah, that's what it is.
Okay, okay.
Mm-hmm. or the parallel, or what's it called, perpendicular component.
So I guess it doesn't really matter which one is, whether, whichever one is pointing up or down, because they're basically equal.
Yeah, it's the same thing. I think just the convention is upwards, but it's gonna equal this because it says the Newton's third law equal and opposite.
Exactly.
Yeah.
Okay.
Can you make sure this is still recording, by the way? Dude, I don't think you were here last time, but I ran out of storage, like, on the very last. Yeah, but like right as I finished.
No, it's fine.
Okay. Let me write a question for you.
But also, what if like sometimes like your triangles just flip the other way, like here,
So you're talking about like this? Like that?
yeah. So the same thing still apply, or you just,
Yeah, it's still cosine theta, like this way, cosine, and this way it's sine.
Okay.
Sine is always sliding, and cosine is the opposite. Here's your question. 10 kilogram block is placed on a frictionless incline at 30 degrees. What is the acceleration of the block as it slides? So basically, what you're gonna do here, your normal force stuff cancels out, it's not gonna affect anything. The only thing, right, it even says frictionless, so I made it really simple. All you're worrying about is the force that's actually moving it, which is the parallel component of gravity. Parallel meaning parallel to this plane. And as I talked about before, sine is sliding. So this is going to be mg sine theta, all right? What is our m? Again, it's 10. I don't know why I keep doing that, but 10 times 10, which is, so let me write units. 10 kilograms times 10 meters per second squared. And then we're dealing with sine 30. So what is sine of 30? I'll just really quickly write this, 1975, 0. All right, whatever. So you might not be able to read this. I'm just doing it for myself, but rewrite that chart if you ever get confused. Sine of 30 is 0.5, right? So what I have here is 10 times 10 times 0.5. So this is 100 times 0.5, which is 50, right? So 50 is the force. 50 newtons is the force overall, right? But basically, what I'm doing here is I'm relating it to mass times acceleration. I kind of did this a long way. I'll tell you like the simpler way, I guess. But I did 50 newtons is the force going this way. So the force of motion essentially, right? And just in general, force equals mass times acceleration. So we can just bring it back to this, right? We know the mass. So we know that 50 equals mass is 10. And then we're looking for acceleration. So you divide by 10. And then you get A equals 5 meters per second squared. So I just did it the long way. The easier way would just to straight up know that F equals M times A, which also equals M times G sine theta. M times A equals M times G sine theta, right? So M and M are the same, they're the same thing, right? So all you're really doing here is making A equal G sine theta. So the only thing you really had to do was look at the gravity or gravitational acceleration, which is 10 meters per second squared, multiply it by sine of 30, which is 0.5, and you would get 5. But it's okay, you don't have to do the short way, that's only if you realize that, but the long way is perfectly fine as long as you don't take too much time, all right? Did I already go over unit conversions? Yeah, actually, this was a long time ago you asked. Yeah, for, I think Kinza, I did unit conversions like very beginning. Just, you can watch the recording after. And then why did I not use mass? Because mass is the same. This is the mass is like 10 kilograms, so 10 kilograms here and 10 kilograms there, it's just gonna cancel out.
If we had to take it into account friction, how would that work out?
Friction, basically, for friction, let me just throw something here. If friction was 10 newtons, then you'd have to cancel this out. So we established that this equals 50 newtons. So the overall force in this direction is 50 minus 10, which is 40, all right? So then from there, you'd have to do this 40 equals mass times acceleration. So if friction is there, then you can't just do this straight up A equals G sine theta. That was just if there's absolutely nothing, no friction. But that's a really good question. One more time, just to say it again. If there's friction, and I use 10 newtons as an example, I have to find the overall, right? They call it the net force in this direction. The net force will be down to the right because it's higher over here compared to here. So the net force would just be this minus this, which is 40. So net force of 40 newtons this way, and then you relate that to mass times acceleration. So in that case, the acceleration would have been 4 meters per second squared. Really good question. All right, next part is my favorite part of this chapter. These kinematic equations. Basically, there's 4 equations that you should know. It's not really related to force. I mean, it can be, but let me write them out real quick. Okay, so here are the 4 kinematic equations you need to know. I feel like there's more, but for MCAT, this is all you need to know. So these, once again, this is not related to force. It can be, but like, you know, like not necessarily. This is just the stuff from before, like velocity, displacement, acceleration, all of that. Each of these equations is missing something, right? So for example, by the way, okay, this V sub 0 means initial velocity, and it's supposed to be VF for the ones that are not 0, but I don't put F just because I feel like, I don't know, it's just harder for me to remember. So if you want, you can include it, or you can just infer that if this doesn't have a 0, it's the final velocity, all right? Also this X, it's technically is displacement, so it's supposed to be delta X. But same thing, when there's too many symbols, I personally forget the equation. So this is, you know, how I read it and how I remember. And it shouldn't affect anything, by the way. Can you see?
Oh, yeah.
Or is it over there?
Yeah.
So this top one, what is it missing? It's missing X, displacement. What is this one missing? The second one, it's missing time. This one, it's missing acceleration, and also like technically initial velocity, but the main thing is acceleration. This one is missing final velocity, all right? So I'll put an actual VF there. Essentially, you'll get different questions, and you have to figure out which of these kinematic equations I want to use, and you can figure it out, all right? So if you have this, like, you know, you have your final and initial velocity, acceleration, and time. Sorry. If you have final and initial velocity and acceleration, you can find this last one, right? Because you have 3 of the components. But if you're given like displacement and, I don't know, let's see, displacement and time and acceleration, you can find out this one, right? Initial velocity. So just practice, I mean, as with all equations for physics, just practice writing them out and just commit them to memory. Definitely kinematics. You know, I don't think it's too bad, to be honest. But like, let me give an example. I have a couple questions for you. I'm gonna leave this question. Actually, you know what? Let me add something to this question.
You said all the x's are all displacement, right?
Yeah, it's supposed to be displacement. It's technically delta x. Okay, you know what we're gonna do? We're gonna start with this before I erase it. I'm gonna add something to the question. And we're taking a look at this right here, this acceleration that we found for the question I'm gonna ask. So basically, once again, use that 5 meters per second squared. I'm asking how much time does it take to slide down, like using the same 5 and 10 or whatever. How much time does it take to slide down 5 meters after being released from rest? So ideally, you're supposed to be able to do this without those cheat sheet equations up there. But for now, since y'all are learning, it's perfectly fine. Just get used to how to use them first, to be honest. So yeah, this is something, if you deal with physics a lot or you've done these kinematics, you'll understand this. But this, okay, we have distance or displacement, right? We have our x. We're looking for a t. We have our accelerations. We have x, a, and t. We also have something else. What else do we have in this equation? I mean, we don't have t, but we're looking for t. But what else do we have in this question?
Initial velocity.
Yeah, initial velocity. Something you have to, I wouldn't call it a skill. It's just like, now you will know if you didn't know. Release from rest, that's your initial velocity. When you're at rest, you're not moving, all right? So your V0, this is your V0, which is 0, all right? Your initial velocity is 0. So which equation are we gonna use? We can use this last one, right? We have our x, we have our V0, we're looking for t, and we have acceleration. So from here, it's just plugging in, all right? So like, let's just solve this. Since this is 0, I'm just gonna completely cancel this whole thing out. That's usually the case, by the way, this equation with the two t's. Most of the time, or at least every time I've seen it on the MCAT, this first one ends up canceling out because V0 usually is from rest. Anyways, we have 5. Whatever this equals. I just speed ran that one. So it's just plugging in, right, in algebra from there.
But if we're missing time, shouldn't we be using the second equation?
No. Okay. This, when I'm saying you're missing time, that means that you don't use that equation if you have time there or if you're looking for time. Because if I'm looking for time, how is this going to tell me the time? There's nowhere, like, whatever I manipulate, like if I bring this to the other side or this to the other side, I'm never going to be able to figure out time from that equation. So that's saying, if you're either looking for time or you're given time, don't use this one. If you're looking for displacement or you're given displacement, don't use this one. That's what this is meaning. Because, if you can find 3 units or 3 variables, you can find the 4th one. That's what's like good about having this many kinematic equations.
So it seems like if you're missing a variable, for example, like the velocity final, then the equation you use must have like all the other variables present in the question.
Yeah, that's how it works. Yep.
Okay.
Skateboard moves 60 meters in 2 seconds, going 500 centimeters per second. What is its acceleration? So figure out which one to use. Try not to look at the cheat sheet, but if you need to, it's okay. All right, if you're still working, just ignore me. But we have distance, right? Or displacement, x, right here. We have time here. Time over here, 2 seconds. And then we have velocity here. We're looking for acceleration. So yeah, I guess this ended up being the same one, that last, the last equation. So anyways, the trick here was that you have centimeters per second. So make sure you don't just plug that in. You have to convert it into your proper SI unit. So it's not centimeters, it's meters per second. 500 centimeters per second is just 5 meters per second. So you can make this 5 meters per second, all right? And then you're just plugging in. Let's write it out now. Since you're moving at a constant velocity, that can just be your initial, not worrying about final or anything. So 60 equals 5, right? 5 times 2 plus a 2 squared over 2. Just cover here. What is the unit for this? Bro, are you serious? Meters per second squared. Did y'all get that? Okay, I'm gonna ask one more question. Because this one, I mean, I trust y'all. I feel like y'all will get it. But like, maybe not. Let me erase. All right, this time I'm gonna erase this. All right, y'all good? Y'all, everybody wrote this stuff down. All right, if you don't tell me, I won't know. I'm gonna erase it. I might or might not have stolen this from like, I think it's a third-party FL. But if a ball is launched straight upward with an initial velocity of 10 meters per second, how high will it go before it falls back down? So same thing as always, think about what you're given and what they equal, or maybe like what you're looking for. This one, if a ball is launched straight upward, this straight up tells us initial velocity, so this is our V0. How high will it go before it falls back down? So how high? It's asking about X. And that's all we're told. We're actually told one more thing. There's two more things that you know, but you're only told like one more of those things. So, that one, like, you don't really, I mean, that one you know, right? It's gonna be 10. Okay, in this case, it's gonna be -10, but I'll get to that. Now for, what is the other thing that you're told?
Straight up.
What is that gonna tell you?
Would it be B final?
And like, what about V final?
It's gonna be 0.
Yeah. So this is asking, you throw it straight up. What happens before it falls back down? When it reaches its highest point, it's gonna have a velocity of 0, right? Otherwise, if it still had a velocity, it would be going up, like keep going up, right? But if it's right about to fall back down, it's up here, velocity 0, and then it falls back down. So you have to like be able to analyze that from this question. So I'll just put here, right? Vf equals 0. Usually our initial velocity is 0, but this time it's your final velocity. Now, okay, for this, the g equals -10. When I first did this question, I didn't use -10, and I'll show you like it. I mean, like technically it wouldn't matter, but you're using -10 because the acceleration, like gravity's pointing downwards. I guess that's why. But let's like put this into an equation. It'll be this, right? So you have 0 squared equals, what do we have? 10 squared plus 2, -10, and then looking for x, right? All right, this is what I got. 5 meters, that's our answer. No, what I was saying was if you didn't use -10 and you just use +10, you would end up with this, 10 squared plus 2 times 10x equals your 0 squared. You get, I'm bringing this to the other side, right? So -100 equals 20x. And then your x value would be -5 meters. The reason I say it doesn't matter is because, at least for this question, the units or the values were like positive numbers. And you can't really say I went -5 meters, right? That doesn't make any sense. So like you can just absolute value that and get +5. So if you didn't know about -10, like yes, -10 is the actual correct value, but like don't worry about like, oh, I don't know when to use it or not. It would give you the same thing technically. Let's talk about the, what do you call it? The relationship between x, v, and a, or position, velocity, and acceleration. Okay, I don't think you could even tell based off of this, because like I'm also confused by looking at this. My calculus is cooked, but Do you know like the relationship just by looking at this? Can anyone tell? I don't even know if this is correct, but can you tell based off of this, anyone, like, what is the relationship between like velocity over time and x over time? I don't know if you can tell. Can you tell? I mean, kind of. Basically, okay, here's what's the actual reality. Velocity is the derivative of x, and a is the derivative of v. So here, v equals derivative of position, and then acceleration is derivative of velocity. I'm talking about like the over time graphs, right? So that also means that velocity is the what of a. By the way, I know like you guys don't want to see calculus on this, like this is the only calculus thing you need to know, but like it's not really gonna affect anything. It just actually makes life easier. But basically, if a is the derivative of v, that means that v is the integral of a. So let me show you like where this will, or two situations where this may come up. One, they'll straight up give you this, right? If you see a graph that's very like sharp, like not sharp, very like, what's the word, like squared off, like this.
Staggered.
Not staggered, but like it's not like pointy or like, no, hold on, I can't speak. It's not like curvy like this, right? When you have something that's like square, it's very easy to find the area or the area under the curve. Do you guys know what I'm talking about? Here, I'll explain it. It's just like if you understand calculus, it would make sense. So if I had this is my a over time, and then this is like, let's just do 10 seconds, and then down here is 20, and this is 50. I have to draw this bigger. Bro, that's not gonna be different. Okay, can y'all see this? This is a 50 and a 20. So 50 over here and 20 over here. Basically, they might give you this, right? Acceleration versus time graph. And they'll just ask you, what is the, I don't know, like overall like velocity or change in velocity like in like at 10 seconds. What you would do is just find the area under the curve. And as I was saying, right? It's very easy to find the area under the curve. By the way, area under the curve is what an integral is. And derivative is like the slope at a given point. So like the slope here would be the point over here or something, right? So when you have something like this where it's very easy to find area, that's most likely gonna involve the area under the curve integral thing. So if they ask you, all you're gonna do is just find this, right? You can break it up into two pieces. So, oh, I didn't even give it, hold on, let's put a 5 over here. There we go, 5s and 10s again. Over here, you'd find the area of this box, which is 5 times 50, so that's 250, right? And then this one, it's 5 because 5 through 10 is 5, and then the y is 20, so this is gonna be 100. And then you just add them up and get 350. I forgot how they worded the question, but like if they're asking something about velocity and they give you acceleration graph, that's what you have to do. Does that make sense? And then, yeah, same thing. Basically, this is the derivative of this, and this is the derivative of this. Based off of that, what can y'all say about, don't look at this. What can you say about the velocity over here, just at this point? Is it increasing, decreasing, or staying the same? So from here to here. This is a position over time graph. What can you say about the velocity there? Yes, it's constant. Once again, even if you hate calculus, just please know derivatives, right? Derivative just means the slope at a given point. So if I have like this right here, this is the derivative at one point, and then over here, and then like that. Do you guys see what I'm doing? So I'm finding the slope at a given point. Basically, this one, this is linear. It's not like curving or anything. So every point is gonna have the same slope, like going like in this direction. So if they gave you this, which they very well can do, right? They definitely can. If they gave you this and ask like what is going on with the velocity at this point, like point A to point B, you would have to know that the slope is not changing there. So your velocity is constant, all right? You're moving the same distance at this over the same amount of time. So that's why velocity stays the same. So those are the two like types of scenarios you could get in regards to position, velocity, and acceleration. Once again, this, hold on.
You could kind of think about it as like driving a car, right? If you just have like cruise control on or whatever, like you're still moving at the same speed.
Yeah.
So if you were to graph it, it would just be like a linear line. But as soon as you hit your gas, you rapidly like accelerate. So there's gonna be a shift in your slope.
Yeah.
Or an upward shift.
Exactly. Yeah, I don't know how to like. Whenever I write things, it never makes sense. So basically, one more time. I mean, it's already written over here, but your velocity is the derivative of your position, and acceleration is derivative of velocity. And then if you go backwards, the velocity is the integral of acceleration, and x, the position, is integral of velocity. So you can either think of it as XVA. I always remember PVA, like PVA graphs and stuff, right? Position, velocity, acceleration, and just remember the order so that you know, like, you know, derivatives and integral. But that's the only calculus you really have to know. But I'm telling you, it like makes life easier. Now there's another term I keep using. I don't think I've said it in a while, but it's the word magnitude, all right? Let's say I have you know what, forget this. All right, I have this right here, and I'm gonna make different sections. Okay, for anyone watching this on YouTube, I'm really sorry, but the worst thing that could have ever happened to me. My phone shut down while recording, and I didn't even realize until the entire lecture was over. So that's why there was a cut here, but we'll just continue straight up. Anyways, luckily for me, I still got a couple students here who missed this part, so at least I'm not teaching to nobody because everyone else is gone. So let's continue, all right? I drew this right here. This is a position versus time graph, all right? And I'm talking about, I don't know what I said, to be honest, before, but I'm pretty sure I was talking about magnitude, the term magnitude, okay? If we look at section B, actually let's look at section C. Is the magnitude of velocity increasing or decreasing? It was a trick question. It's decreasing, right? Let's look at this. What did I say? I said velocity is the derivative of your position over time graph. So basically, we're looking at C, right? I'm just gonna redraw this over here. The curve looks kind of like this, right? Basically, down here, like from the very start, what is derivative? It's like the slope at different points, right? So your slope looks like this. Then as you're going along, look at my slope, it's flattening out, it's decreasing, all right? Now here's the thing, this first slope, we can just make something up. Let's say it was like 30 meters per second, that's our slope, that's our velocity. Over here, when we reach there, it's about like, let's just say 5 meters per second. So both cases, right, 30 and 5, they're still positive slopes. However, since I decrease from 30 to 5, my overall magnitude is decreasing, okay? Now let's look at E, section E. What does this look like? The curve, let's draw it over here. It looks like this. It's kind of like the opposite, right? So your top point, the slope would be like kind of flat-ish, and then it's increasing, and then by the time you're here, it's really, really steep. However, both, or actually all of these slopes, right, they're negative, so your velocity is negative. So let's just throw out random numbers again. The top one, maybe it was like negative 2 meters per second. And then this bottom one, maybe like negative 14 meters per second. So overall, I have a negative velocity. And on top of that, my negative velocity, it's decreasing, right? I went from negative 2 to negative 14, smaller. But in section E, my magnitude is not decreasing, my magnitude is increasing. Okay? Magnitude, we're just looking at value itself. So think about absolute values. Okay? Think about it like this. I became more negative. I'm already negative and I became more negative. My magnitude increased. My magnitude of negative number increased. Over here, I'm dealing with all positive. That one is probably easy. ish, right? You went from a positive to a less positive. But I guess the trick there was that you're still positive. So when you're determining if magnitude increased or decreased, you're not looking at the fact that I'm positive or negative. You're looking at how much I changed from the beginning to the end, okay? So section C went from a number to less positive, right? So we said 30 to 5, magnitude decreased. Now section E, where our velocities are negative, our magnitude increased. We went from -2 to -14. And if you're looking at absolute value, all this is 2 and 14. So my magnitude increased, okay? Does that make sense? So yeah, just be like mindful of these terms, magnitude versus like actual values. Really quickly, just want to bring up circular motion. Just drop in a formula here. I think it's like centripetal or centrifugal, I don't remember the term, but the force, like the circular force, is equal to mv squared over r. I don't think I've ever used this formula. Maybe I saw it in one question and I got it wrong because I didn't know. But know this formula, the most I can see them doing with it is making you equate it to m times a, right? So this is also equal to force, and so is this. So I can see them giving you some situation or some scenario where you have mv squared over r, and maybe you have to figure out acceleration or something. So, you know, if you look at this, mv squared over r equals m times a, cancel out the m's, v squared over r gives you a. So yeah, I guess be able to manipulate this formula a little bit, but I'm not gonna talk too much about it. What I do want to talk about though is torque. This is our last like main topic for today. So torque, the formula for torque is RF sine theta, okay? RF sine theta. I don't think this is that big of a deal, but when we look at work equals force times distance, right? It's force, so newtons times distance, the unit is like meter, right? So newton times meter. And work, the actual unit for it is joules. So newton times meter equals joules. Look over here, RF sine theta. R, we're gonna talk about what exactly R means, but R is a distance, which is measured in meters, multiplied by force, which is newtons, or you can write like this, newton times meter. And sine is just gonna change your value, it's not a unit, right? So this is also newton times meter. However, for some reason, we don't look at torque as measured in joules. Like apparently it's just wrong to say it's measured in joules. We just say a torque, the value is newton meter, right? So instead of 10 joules, we say 10 newton meters. I don't think it's that big of a deal, but just bringing that up. So the main time we deal with torque on the MCAT is the seesaw thing. All right. Let's say, let me draw this bigger. Let's say I have a 10 kilogram block and it's placed, there you go, I did 10 again, oh my God. All right, the 10 kilogram block is placed, I don't know, let's just do 6 meters away from the fulcrum, right? This is the fulcrum. Fulcrum is just another word for the center. If I just put this 10 kilogram block on there, what's gonna happen? It's gonna tip down, okay? So the question that's usually asked is, where would I put this, let's do 45, okay? Where would I put a 45 kilogram block such that my seesaw is balanced? Would I put it 10 meters away? Would I put it 0.5 meters away? Where would I put it? Okay? So in this question, I brought up this formula, RF sine theta. What the sine theta is referring to is the angle of force. Like, where are you putting the force? Think about this. If I have a box and I'm putting it down, the angle is like this, right? It's vertical. And with respect to this horizontal axis, right, it's just a 90-degree angle. And so sine of 90 is 1, hopefully. Otherwise, we just not get any values, okay? So that's what the angle is referring to. I'm putting a box just straight down. That's a 90-degree angle with respect to this parallel, or well, not parallel, but horizontal axis, okay? So for these seesaw questions, you never really use degrees. I'll show you where degrees could show up. But anyways, what you're gonna do here is you're essentially equating two sides, right? You have RF equals RF. So R1 F1 equals R2 F2. So this will be for the 10 kilogram block, and this will be for the 45 kilogram block. So what I'm gonna do here is the R is gonna be 6, right, for this side. So 6 times force is going to be, it's basically 10 times 10, right, which is the G. You don't really have to find the force, you can just look at the mass itself, because this one you're also multiplying by 10, right? So 45 times 10 and 10 times 10, it's just the same ratio, right? If you want, you can do it 100 and then you'll get like 450. But once again, it doesn't matter, the ratio is still the same. But I guess just to be, I'll just do it. But once again, you do not have to. So let's put 6 times 100 equals R2 times 450, right? These are newtons, by the way, the force. And then this is just algebra. So 600 equals okay, so I got about 1.3. If I did my math wrong, I'm sorry, but this is the method to do it, okay? So basically what this is telling me is that I want to put my 45 kilogram block 1.3 meters away from the fulcrum. So maybe like right here, I'll put it right here. And then this distance would be 1.3 meters, okay? If I do that, if I put this 45 kilogram block 1.3 meters away from the fulcrum, while this 10 kilogram block is 6 meters away from the fulcrum, I will have a completely stable, or this will be in equilibrium, right? It's not going to be tipping to either side. It's going to be completely stable at equilibrium. So that's pretty straightforward. But I want to emphasize something. This R refers to distance from the center, right? Or distance from fulcrum. Let's write that down. The reason I'm bringing this up is because I have seen them try to trick you. They'll give you this thing, okay? They'll tell you you have a 100 meter long beam, okay? And the fulcrum's in the center. So this entire thing is 100 meters. And then they'll tell you that your 10 kilogram block is placed, 20 meters from the end, okay? So they're gonna, you have to visualize this, but a 10 kilogram block, they're gonna say it's 20 meters from the end. What does that mean? It means 20 meters from this end, all right? So I'm 20 meters. However, when you're doing this RF stuff, your R is not 20. What is your R gonna be? Look at this. Your entire beam is 100 meters. So that means this half is going to be 50 meters, and this half will be 50 meters. If my block is 20 meters from the end, that means that I am 50 minus 20? I am 30 meters from the fulcrum. That is our R value, the 30, okay? So for a question like this, if I'm trying to find torque just by this 10 kilogram block, you would just do 10 times 10, which is gravitational acceleration, and then times this 30 meters. You understand? Now, this, as I was saying, this is pretty much the only time I really see torque on the MCAT. But let me talk about where does torque what does torque really mean? Think about this. Let's say I have a block here, and this is the center of mass, right? It might be up here, but if I'm pushing it like this, if I'm just pushing it straight up by the center of mass, what's gonna happen? It's going to move, right? It's going to move. However, if the center of mass is here, and I, maybe push like this, you can say it's angled or whatever, but I'm not pushing at the center of mass, what's gonna happen? I don't know if I can, no, it's not gonna work. But if I push someone that's not the center of mass, I'm just gonna rotate, right? This will rotate, and I'll get like, oh my god, hold on. Right? It will rotate like this because I'm pushing it this way. So you can calculate torque, right? Let's say I'm using like 20 newtons of force at an angle of, I don't know, let's just do 30 degrees, right? This is the angle like between this and the box. And then I am, I don't know, like 2 centimeters away from the center of mass. All right, so this is 2 centimeters. They might ask you, what is the torque exerted on this box? Let's calculate that. All right, torque equals RF sine theta. Your R is 2 centimeters. Remember, SI units are meters. So that's going to be 0.02 meters. All right. Your F, they told you 20 newtons, so you're going to put 20. And then you're doing sine of 30. That's the angle that you're pushing it, right? You're not pushing it like straight up like this. You're pushing it like at an angle. And then obviously this is definitely not to scale. Yeah, I don't know. Anyway, sine 30. What is sine 30? Someone tell me. You can look back at your notes, the 1975 thing that we talked about. You have, what is it? 5 options, and it's definitely not going to be 1 or 0, so you pretty much have 3 options. 0.9, 0.7, 0.5. If you didn't write it, you should write it, you know what I'm saying? Yes, 0.5. So what we have overall is 0.02 times 20 times 0.5. What does this equal? It's just 0.2. This is the torque, and then once again, it's Newton meters, not really joules. Okay, so that's where torque can show up. Once again, I know I keep saying once again, but this is like the main situation or scenario where you will see torque. This was the main thing that I missed. Just some terms real quick. Let me write some. We got translational equilibrium, and then rotational equilibrium. So translational equilibrium just refers to when I have no net forces acting on me. All right, so the cop was about to kick me out, bro. So no net force. All right, then this rotational equilibrium means no net torque is acting upon me. So for this translational equilibrium, think about this like translation. I mean, I don't know if you think about it like this, but I think about movement with translation. Like I'm translating this way. I don't really know if that made sense. Rotational, I think about the torque square that I showed you, how I was rotating it. So this one's related to torque, this one's related to force. Translational equilibrium, from what it seems, it's related to Newton's first law, where an object in motion stays in motion unless it's, you know, and encounters some external forces that cause a net force, right? Basically, right, you're moving. If you're moving like 5 meters per second and nothing is touching you, right? No air resistance, no friction, no external people, whatever, then you have a net force of 0, right? Nothing is pushing you this way, nothing's pushing this way, nothing's this way, whatever. You're in translational equilibrium. But once something happens, like maybe friction starts opposing you, then you're no longer in translational equilibrium. And then rotational equilibrium is just kind of like that, but for torque. So if I'm like pushing then I'm not in rotational equilibrium because there is a net torque, right? Whatever it was, like 0.2. But if I'm not doing it, then you're in rotational equilibrium. You're not like rotating or anything. But this also means that you can have torque, right? Like it doesn't have to be zero. It's just the net torque has to be zero. So I could be pushing this way. And then if I do the opposite of that, which I could be, I don't know, I think it's like this way, right? If I do the opposite of that and it's completely identical, I still have like different torques acting on it, but just the net torque would be zero. So as a result, right, if you just had this force pushing on it this way, you would rotate. But if you had the exact same on the opposite side, then there would be no rotation because it cancels out, okay? So that's rotational equilibrium. Yeah, now we're pretty much done. I just wanted to add something, kind of going back to force and just units. Remember I told y'all units are very important. Like you should know your units, if anything, formulas and units, all right? When I say that, what do I mean? I gave that example of volt over meter equals Newton per Coulomb, right? That can help you a lot in the question that involves those. However, let's talk about what we're currently on, which is forces. Force equals mass times acceleration, and this gives you newtons, right? But what is a newton? Rather than just saying I get newtons, what is a newton made of? Look at this. Mass is kilogram. Acceleration is meters per second squared. I'm multiplying these two to get newtons. That means that a newton is kilograms times meter per second squared. Okay? What's next? What's after force? We have work or energy. Work is force times distance. And yes, there might be like a cosine and stuff, but I'm just talking about in general, it's force times distance. This will give you joules. But what is a joule? Well, we said that force, which is newtons, is kilograms times meters per second squared. And distance, or displacement, whatever you call it, is meters. So kilogram times meters over second squared. So it's kilograms times meters squared over second squared, all right? This is what work is. Now the third one is power. Power is joules per second, all right? So if a joule equals this, and I'm just dividing by seconds, I have the same thing, kilograms times meters squared over second, but it's cubed now, all right? Seconds cubed. And power is measured in watts, by the way. Don't get this confused with work. This is just the unit watts. So the reason I bring this up is because I've actually seen, it might have been on AAMC, but they'll ask you something like this, like, they'll give you 4 choices and they'll ask you which of these cannot be used to represent force or to represent energy, okay? Let's just talk about force. They might give you one answer choice as Newton, and then they'll give you one as this right here, kilograms times meters per second squared. And then they might give you something random like pound times foot over minute squared or something. I don't know if this one works, but like that one like might be iffy. You can just check the other ones. I think from what I remember, there was like a choice where you could tell it was off. Like the choice D was related to work or power. So you can kind of like, obviously, A and B represent force, so you can get rid of those. Between C and D, you can just process elimination. If you don't know about C, just leave it alone. D, if it's completely wrong, then you know that D is your answer, okay? Does that make sense? Yeah, so anyways, throughout, I will just try to make different connections on like what units can mean, all right? Okay, officially done. If this video did not record, I'm not recording this, bro. I'm just dropping this entire course. Let's see. Moment of truth. Let's go.